Hello everyone and welcome to the latest installment of the A-Level 9709 Solution Guide series. In this video we will take a closer look at paper 1-2 from the May-June exam period of 2021. So without further ado, let's get straight into it. In part A of exercise 1 we are supposed to express 16x squared minus 24x plus 10 in form 4x plus a squared plus b. To find our value for a, we will do the following. Coming from the angle that a whole square comes generally from the expression a plus b squared, which in turn equals to a squared plus 2ab plus b squared, we will now attempt to figure out this value b, which is called a in this exercise. So although this might appear to be a bit confusing at the beginning, please do not get confused by this. So in order to determine this value, we can make use of the knowledge that 2ab is represented by the expression negative 24x. Therefore, negative 24 equals 2 times a. A squared is 16x squared, and it's sufficient for us to simply focus on the coefficient, namely 16, and take its square root, which is 4. Now we are able to solve the equation for b, which will represent our value for a, and after rearranging this equation for b, we can conclude that our b contains the value 3. By our b, I mean what is called a within this exercise. Now to determine b, we can simply use our solution in order to complete the square using the method provided. And after transferring the expression within the brackets into a whole square expression, we can conclude that b is positive 1, since 10 minus 9 equals 1. Therefore, we have provided the expression from the outset of the exercise in the desired form. In part b, it's stated that it is given that the equation 16x squared minus 24x plus 10 equals k, where k is a constant and has exactly one root. We are supposed to find the value of this root. So what we first do is rearrange this equation in a way that it represents a quadratic equation rearranged for 0, and from this stage we are able to work with the quadratic formula provided. So our coefficients a, b and c are 16, negative 24 and 10 minus k respectively. Since it's stated that this equation possesses exactly one root, we can derive from there that this translates into the discriminant being 0, since if it's negative we would have no solution, and if it were to be positive we would have more than one solution, namely 2. So in order to, in a first step, find our value for k, we can simply plug in our values for a, b and c accordingly and rearrange this entire equation for k, which will let us conclude that k equals 1. Using our result from exercise A will aid us in finding the value for x. This will help us in rephrasing this equation as follows. In the first step we will substitute 1 from both sides of the equation, take the square root and rearrange our equation for x, delivering us its value, namely 3/4. Moving on to exercise 2, where in part A it is stated that the graph of y equals f of x is transformed to the graph of y equals 2f of x minus 1. We are supposed to fully describe the two single transformations which have been combined to give the resulting transformation. Looking at the expression within brackets, where it's stated that x is negative 1, we can conclude that the translation that occurred there can be represented by the vector 1, 0, since in order to get 0 returned as a result for the expression inside of the brackets, we would have to subtract 1 from 1. There are no transformations along the y-axis, since for that to happen we would have to find the addition or subtraction of a constant c, which here is not the case. Additionally, we can state that compared to the original graph, the transformed graph is stretched by factor 2 in y direction, which can be thought of as the amplitude of a trigonometric function depiction provided. In part B of the exercise, it is stated that curve y equals sine of 2x minus 5x is reflected in the y-axis and then stretched by scale factor 1/3 in the x direction. We are supposed to write down the equation of the transformed curve. So firstly, in order to reflect any curve in the y-axis, we simply have to multiply its equation by -1, which is fulfilled by just putting brackets around the expression and put a negative sign in front of it. To stretch our curve by scale factor 1/3, we will have to multiply each expression within this curve that contains x to multiply by 3, which sounds a bit counterintuitive, but we can think of it in terms of having to multiply those segments of the expression with the reciprocal of the scale factor. So certainly the reciprocal of 1/3 is 3/1, which is 3, so we multiply 2x within brackets with 3, as well as the expression negative 5x. With 3, don't be confused of not encountering a negative sign in there. The reason for that being that due to its reflection in the y-axis, the entire expression has been multiplied with -1, and we multiplied the expression -5x also with 3. After expanding our bracket, meaning multiplying each summand within it with -1, we can conclude that the equation of the transformed curve is represented by the expression negative sine x plus 15x. Moving on to exercise 3, where we are presented with the equation of a curve y equals x minus 3 multiplied the square root of x plus 1 plus 3. The following points lie on the curve and non-exact values are rounded to 4 decimal places. In part A, we are supposed to find k, giving our answer correct to 4 decimal places. So to find our value for k, we simply substitute x for 2, and after rounding correctly to 4 decimal places, we can conclude that its approximate value is 1.2679. Keep in mind, to find the correct answer to 4 decimal places, we'll have to look at the 5th decimal place after the decimal point, and we would have to round the value in the 4th decimal place after the decimal point down, which means it would remain what it is for values between 0 and 4 included, and for every value that's larger than 5, we would have to round this digit up. Part B of exercise 3 requires from us to find the gradient of AE, giving our answer again correct to 4 decimal places. This is done using the formula for finding gradients when 2 points are provided as shown. This will then in turn let us conclude that the gradient of AE, correct to 4 decimal places, is 1.7321. Moving on to the next segment of this exercise, it is stated that the gradients of BE, CE and DE rounded to 4 decimal places are as follows. We should state, giving a reason for our answer, what the values of the 4 gradients suggest about the gradient of the curve at point E, and what we can observe looking at the coordinates of those 4 points in conjunction with the gradient of the curve when we get closer and closer from A to D towards point E, is that the gradients suggest that the gradient at point E is 2, since the changes are getting smaller and smaller the closer that we get towards point E, and that additionally the x value tends to 3. So our changes are getting smaller and smaller, and the gradient will reach its limit for the value 2. Next on to exercise 4, where it's stated that the coefficient of x in the following expansion is p. The coefficient of 1 over x in the expansion of the following expression is q. Given that p equals 6q, we are supposed to find the possible values of k. So in step 1, we will find the coefficient of x in this expansion, making use of Pascal's triangle provided. We can hold our expansion after the second summand, since x squared divided by x equals x, and we are just supposed to find the coefficient of x, which is nothing else but 3 multiplied 16 multiplied 10, being 480. Similarly, to determine q, we will apply the same method as above, and here we can stop after having calculated the third summand of this expansion, knowing that we are looking for the coefficient of 1 over x, and this stage is reached after dividing x cubed by x to the power of 4. Therefore, the value that we are looking for is represented by the expression of 10 multiplied 8 multiplied k squared, which means that q is represented by the expression 80k squared. To now find the value of k, we can make use of the given fact that p equals 6q, which we can now easily do since we have determined the values for both of those variables. We would simply equate p for 6 times q, and rearranging it for k delivers us 2 possible values for k, namely negative and positive 1. Which brings us to exercise 5, where the function f is defined by f of x equals 2x squared plus 3 for values of x being 0 or larger. In part A, we are supposed to find and simplify an expression for f of x, and to perform that, we will replace x of the outer function with the expression of 2x squared plus 3. Applying the whole square formula and thereafter expanding our brackets will let us conclude that the simplified version of the expression f of x can be represented by the expression of 8x to the power of 4 plus 24x squared plus 21. In part B, we are supposed to use that exact equation and equate it with 34x squared plus 19, and after simplifying and rearranging this equation for 0, we will receive the preliminary result of 4x to the power of 4 minus 5x squared plus 1. We should realize that we are working with the biquadratic function, since the exponent of x to the power of 4 is is twice as large as that of the exponent of the expression x squared. 2 multiplied 2 equals 4. We can now apply the rule provided in order to rephrase this equation in a way that allows for us to factorize the left-hand side of this equation, leading us to the equation being rephrased as 4x to the power of 4 minus 4x squared minus x squared plus 1. Taking a look at the first two summands of the left-hand side of the equation, we should realize that we can factorize both of those with 4x squared, and in the lattice section we can simply factorize negative 1, leaving us with two exactly similar expressions within the brackets as desired. In a final step we can factorize this expression further by the aforementioned expression within the brackets, which leaves us with a multiplication having the result 0, and a multiplication can only yield the result 0 if at least one of its factors is 0. So we will explore this for both brackets separately. So for the first bracket we can determine that x is either positive or negative 1 over 2, and for the second option that x is either positive or negative 1. Since on the outset of this exercise it was stated that x can only contain the values 0 or larger, we will have to discard all of our negative solutions, leaving us with the two positive solutions for x, namely 1 over 2 and 1. Next on to exercise 6, where it is stated that points A and B have coordinates 8, 3 and PQ respectively. Furthermore, the equation of the perpendicular bisector of AB is represented by the equation y equals negative 2x plus 4. It's our task to find the values of P and Q. Since P and Q are both unknown, we will have to set up two simultaneous equations in order to find their values. From the statement that the equation of the perpendicular bisector of AB is y equals negative 2x plus 4, we can conclude that the gradient of AB is 1 over 2, applying the formula provided. Thereafter we can set up the equation that 1½ must be Q minus R over P minus Q, as per the guidelines on how to find the gradient between 2 points as per the formula provided. At this stage we will attempt to simplify this equation as far as possible, and we will halt after the stage where it's stated that 2Q equal P minus 2. What we have to do now is to set up a second equation as stated above, and again we will make the use of the information that we are provided with the equation of the perpendicular bisector of AB, meaning that when we were to look at a line AB, the perpendicular bisector would bisect this line right in between A and B in a right angle. So what we are doing at this stage is equating the y coordinate of our midpoint with the right hand side of this equation by substituting x for the x coordinate of our midpoint, and we will subsequently rearrange this equation for Q. Now we have set up two different equations, each of which are containing P and Q, so we can substitute now the expression negative 11 minus P for Q in the first equation, which will help us in determining the value of P. In the first step we will expand the brackets and thereafter rearrange this equation for P, which has the value negative 4. To find Q we can now replace P for negative 4 and thereafter conclude quickly that the value of Q is negative 3. Moving on to exercise 7, where it is stated that the point A has coordinates 1, 5 and the line L has gradient negative 2/3 and passes through point A. A circle has center 5, 11 and a radius of the square root of 52. In part A we are supposed to show that L is the tangent to the circle A. This can easily be established as follows. Let's imagine that we are provided with a circle and we are looking at a tangent at point A. We already know its gradient, and for L to indeed be a tangent to that circle, this gradient needs to be perpendicular to the radius from the center of the circle towards point A. Therefore we firstly calculate a gradient of AC, C being the center of the circle, using the formula provided. After simplifying this expression we can determine that the gradient of AC is 3 over 2. So for those two lines to be perpendicular to one another, its multiplication needs to provide us with negative 1 for its solution as per the guidelines provided, and this is indeed the case, and therefore both of those lines are perpendicular to one another. Thus L is indeed a tangent of the circle in A. In part B of exercise 7 we are required to find the equation of the other circle of radius square root of 52, for which L is also the tangent of A. So we could imagine for this to look like the sketch down below. So the point where L touches both circles will be A again, and C will be the center of our original circle. And in order to find our other center, we will have to move from A in the direction of vector CA. Vector CA would be this vector here, and adding CA another time to our point A will provide us with the coordinates of the center of the other circle. Let's call it C1. Doing so lets us conclude that the coordinates for the other center of this circle is located at -3, -1. Therefore, the equation of that circle must be x plus 3 squared. Therefore, the circle is represented by the equation x plus 3 squared plus y plus 1 squared equals 52. Next on to exercise 5, where it's stated that the first, second and third term of an arithmetic progression are a, 3 over 2a, and b respectively, where a and b are positive constants. The first, second and third terms of a geometric progression are a, 18, and b plus 13 respectively. In part A, we are supposed to find the values of a and b. In the first step, we are collecting all of the information provided concerning the arithmetic progression and state the values of its first 3 terms. Next, we will attempt to discover the common difference of this progression, which is done by subtracting the preceding term from its successor. Therefore, we can set up 2 different occasions concerning D, namely the second term minus the first term and the third term minus the second term, providing us with a simplified solution that D can either be represented by the expression 1 over 2a or by the expression b minus 3 over 2a. To express b in terms of a, we will simply equate both of those statements with one another and conclude at this stage that b can be expressed as 2a. We will apply the same method for every information that we could gather from this exercise concerning the geometric progression, and here again we will firstly state the first 3 terms of this progression. The difference being that since we are dealing with a geometric progression, that we will have to find the common rate, which is determined by dividing a term by its predecessor. Therefore, we can either express r by dividing the first from the second term or the second from the third term. Since 18 over a and b plus 3 over 18 both represent r, we can equate those, and we will also rearrange our equation for b in order to be able to calculate the value for a. Therefore, 324a minus 3 equals 2a, and we will arrange this equation until we receive a quadratic function, which we then can solve using the formula provided. We are getting 2 values for a, namely 12 and -54 over -4, which means that only 12 is a valid solution for a, since it's stated that a and b are positive constants. Now that we have found a, we can simply substitute 12 for a in either of these expressions, whereby it's easier to operate with this one here, meaning that the value of b is double the value of a, and since a is 12, b must consequentially be 24. In part B of the exercise, we are supposed to find the sum of the first 20 terms of the arithmetic progression. To achieve that, we need firstly to determine d in order to be able to use the formula provided, and this is achieved by subtracting the first from the second term or the second from the third term. We will here work with subtracting the first from the second term, which is the same as half of a, and since a is 12, our solution must be 6. Now we can plug in the values into previously provided formula and therefore conclude that the sum of the first 20 terms of the arithmetic progression is 1380. Next on to exercise 9, where we are provided with a graph that shows part of the curve with the equation y squared equals x minus 2 and the lines x equals 5 and y equals 1. The shaded region enclosed by the curve and the lines is rotated through 360 degrees around the x-axis. We are supposed to find the volume obtained. In order to discover the lower boundary of the rotational volume of this shape, we will investigate the intersection point of the line y equals 1 with that of the curve. This is done through equating both statements. We already know, since y equals 1, that we can replace 1 for y, therefore 1 squared equals x minus 2, and rearranging for x provides us with the x coordinate of the intersection point, which is 3. Next, using the formula provided, we can set up the equation that needs to be integrated in order to find the volume obtained, and this is done through applying the power rule onto both summands within the brackets, and after plugging in the upper and lower our boundaries for x, we'll be able to conclude that the size of the volume obtained is 4 pi. So far we have calculated the rotational body including the shaded rectangle. So what we now need to do from this result is to subtract the volume of the similar that would emerge if we were to rotate the rectangle. The formula for calculating the volume of a cylinder is pi multiplied its radius multiplied its height. The radius will be 1. Please don't mistake it for 0.5, since after rotation this will actually expand further outside. And the height can be calculated by subtracting 3 from 5, since we have determined that the intersection point between the curve and y equals 1 has the coordinates 3, 1. Thus we can simply subtract 3 from 5 to determine our height. This will let us conclude that the volume of the cylinder is represented by the expression 2 pi. So now we just subtract the volume of the cylinder from that of the entire body here and conclude that the volume obtained as described above is 2 pi. Moving on to exercise 10a, where we are supposed to prove the following identity. For that we will just inspect and transform the left-hand side of this identity until we obtain something that looks exactly the same to the expression on the right-hand side of it. In step number 1 we will transpose those two fractions into a single one by applying the method of cross multiplication and obtain the following expression. Next, using the whole square formula, we will expand each of those brackets and also simplify the expression of the denominator, which simplifies down to 1 minus sine squared x, since we will apply the formula provided. Next, we simplify the numerator for as much as we can, with just 4 sine x remaining, and furthermore transform the denominator once again, applying trigonometric identities after Pythagoras provided. So at this stage we can realize that we are almost there. So in a final step we will convert this fraction into a factor of 2 separate fractions, where we can finally make use of another trigonometric identity, namely that sine x over cosine x equals tangent x. So here we can finally conclude that the left-hand side of the identity indeed is nothing else but the expression provided on the outset of this exercise, which was to be shown. Next on to part B of exercise N, where we should follow through on exercise A and solve the equation provided for x being within the interval 0 and 1 over 2 pi included. So as mentioned, following through on A, we can substitute this expression for 4 tangent x over cosine x, since those two expressions are identical, and equate those for the expression 8 times tangent x. In the next step we will rearrange our equation for cosine x and simplify the right hand side of the equation. Now using our calculators, and please be mindful of what mode it is in, needs to be set to radians, we should conclude that this equation has a solution for x equals 1 over 3 pi. This leads us on to exercise 11 of this exam paper, where the gradient of a curve is given by the first derivative of its function, which is expressed by 6 multiplied 3x minus 5 cubed minus kx squared, where k is a constant. Additionally, the curve has a stationary point at the coordinates 2 and negative 3.5. In part A we are supposed to find the value of k. For this we can make use of the following fact. It is stated that the stationary point is at coordinates 2 and negative 3.5, which means that the first derivative of 2 equals 0. Therefore, we just substitute 2 for x and equate it with 0. Thereafter, we rearrange our equation for k and conclude that k has the value 3 over 2. In part B, we're now supposed to find the equation of the curve. We have already been provided with its derivative, so we will have to integrate this expression, and we have just figured out in the previous part of the exercise that k is 3 over 2, so we just substitute 3 over 2 for k. Moving on to part B of this exercise, where we are supposed to find the equation of the curve. So what we have to do is to integrate the function of the first derivative, and since we've already figured out the value for k, we can substitute k for 3 over 2. We will integrate the first part of this expression using the chain rule provided. The most important part of that is that we should not forget to counteract the derivative of 3x, which would be 3. So to do that, we will have to multiply it with its reciprocal, which is 1 over 3, since the number multiplied by its reciprocal always equals 1 and doesn't change the value of the expression at all. For the latter part, we just need to make use of the power rule for integrations as provided. Simplifying the equation will deliver us the following following expression, whereby the value of c still needs to be determined, and to make that happen we will make use of the fact that we already know at least one point of this curve, which is its stationary point. So we will simply make use of the equation that f of 2 equals -3.5, whereby we will substitute 2 for x. And thereafter we will just rearrange our equation for c, which happens to be 0. Therefore the function of the curve is 1/2 multiplied 3x minus 5 to the power of 4 minus 1/2 x cubed. Part c of this exercise requires from us to find the second derivative of the curve, which we can do by simply following through from our knowledge of the equation for its first derivative. And here again we will have to, which is again done with the help of the chain rule and the power rule for derivatives. Simplifying our expression lets us conclude that the second derivative of the curve can be expressed by 54 multiplied in brackets 3x minus 5 squared minus 3x. In the final part of exercise 11 we are now to determine the nature of the stationary point at the coordinates 2 and -3.5, and this is done through substituting 2 for x in the second derivative, whereby we receive a positive number, meaning this means since 48 is positive that therefore the nature of the stationary point is that it represents a minimum. We have now arrived at the final exercise of this exam paper, namely exercise 12, where we are provided with the following diagram, which I have already prepared in order to explain processes necessary in order to solve the subsequent exercises. In part A of this exercise we are supposed to show that angle PAQ equals 1/3 pi radians. The angle in question can be found here as highlighted, and in order to tackle this issue we can count the number of instances that this shape occurs within this entire diagram, and we can see that it occurs in total 6 times, each of those representing 1/6 of a circle with the same radius. We know that the angle of an entire circle has the size of 360 degrees, and since we are operating in terms of radians we need to transfer that number into radians, which is 2 pi. Next, since we are working with just 1/6 of a circle, we simply divide 2 pi by 6, which equals pi/3, meaning that we have shown what was stated on the outset of exercise A. In part B we are now supposed to find the length of the rope that is represented by the perimeter of this entire diagram. We know that the radius of each pipe has the size of 20 centimeters, and we should see that when we put 2 radii together that we are getting a representation of the straight parts of the row around this diagram. This again occurs 6 times in total, and since 20 plus 20 equals 40, this part of the rope can be calculated by multiplying 6 by 40. As for those arc lengths, we have already determined that all of those 6 circle segments make up for an entire circle, so we simply need to calculate the circumference of a whole circle, or we can just calculate 6 times the arc length of each circle. Either way, we have to multiply it by the radius, which is 20, and after simplification we can conclude that the length of the rope can be represented by the expression 240 plus 40 pi. Moving on to part C of exercise 12, where we are supposed to find the area of the hexagon ABCDEF, providing our answer in terms of the square root of 3. The hexagon in question is highlighted in purple, and we can also see that the hexagon consists of 6 congruent equilateral triangles. Therefore our strategy will be to calculate the area for one of these triangles and multiply the result by 6. Therefore we are multiplying 6 by the angle of one of those aforementioned equilateral triangles. We know from part A of this exercise that each angle in question has the size of pi/3 radians, and we will be applying the trigonometric formula for calculating the area of the triangle provided. After simplifying our expression, we can see that the area of the hexagon is 2400 times the square root of 3, which fulfills the requirement of this task that our answer needs to be provided in terms of the square root of 3. Finally, we are supposed to find the area of the complete region enclosed by the rope. So to do that, we can dissect this entire diagram into 3 types of shapes. Firstly, the hexagon, and luckily for us, we have already calculated its area in the previous part of this exercise. Furthermore, it consists of 6 identical rectangles and the area of our circle. Therefore, we can determine the complete area enclosed by the rope by adding up the area for the hexagon plus the full circle plus 6 times the aforementioned rectangles. The result for the hexagon we can simply copy over from C. The formula to calculate the area of a full circle is pi multiplied its radius squared, the radius being 20, and the length and the width of the rectangle are 20 and 40 centimeters respectively. Putting everything together lets us conclude that the area of the complete region enclosed by the rope is 2400 times the square root of 3 plus 400 pi plus 4800 centimeters squared. I've been your host Marco from Planet Maths. Should you derive any value from my videos, please consider to leave a like, comment and subscribe. Thank you for watching. Cheers!